Hi Year 13. In this video I'm going to round off yesterday's work on integration by reversing the chain rule, and then we're going to move on to a new technique for integration called integration by substitution. Now, if you were confident with yesterday's work, feel free to skip ahead through this first part of the video because I'm going to go through a few examples so that those people that need extra practice can see me doing a few more of these and can have a go themselves. There's some on this PowerPoint here for Dr. Frost, and these 5 I'm going to go through. If you want to go back to a previous slide, there's some more over here, and you can check your answers by uncovering the boxes. And then at some point after, in a while, I'm going to go through this part as well because it's got something to do with sec as well. Okay, so I'm going to start with these ones. Remember, we're looking out for particular forms for our integrals. There's about 3 or 4 different types that we've come across so far that lead us to try particular educated guesses for our integrals, for our answer, and then we try it and then we adjust based on what we get when we differentiate. So when I look at this top left one, I can see sine x next to an expression with cos x to the 5. So sine x, I notice, is almost the derivative of cos, okay, up to a scalar multiple, okay. It's meant to be minus sine, but sine is roughly speaking the derivative of cos. And this has been raised to the 5. So before this entire thing has been differentiated, we reckon it's probably something like cos x plus 1 to the power of 6. Okay, and the reason for that is because when you apply the chain rule to this, the 6 will come in front, it will knock down to a 5, which matches this 5, and then out of the bracket is going to come minus sine x, which is going to match closely to the sine x that's already there. Okay, so we're going to try this, see what we get when we differentiate, and then suss out how to adjust and compensate. So, chain rule will say 6 at the front of this bracket. Bear in mind, I'm differentiating this way around. Here, 6 goes down to 5, and then out of the bracket comes minus sine x. Like that. Right, if I tidy up, I can put things at the front to get it to match this stuff. So this is minus 6 sine x, cos x plus 1 to the 5. Now, this mostly matches what I've got at the top, except the only difference is my constant at the front, which gives me minus 6 times what I'm supposed to get in this integral up here. So to adjust, we're going to divide by this minus 6, and that's going to cancel it away. So my integral, let's star this so I can refer back to it. So the integral is, in fact, minus a 6th times cos x plus 1 to the 6, and then plus c. There we go. Okay, so that's one of these done. And again, for all of these, if you differentiate your answer, you can check it goes back to what's up there. Right, secondly, I've got cos x squared on top of 2 plus cot x to the 3. Again, I'm trying to spot things that are derivatives of something else that appears. So I can spot here that cos x squared is roughly the derivative of cot x. Okay, if we remember, cot x differentiates to minus cos x squared x. So again, that's roughly the derivative of that. But this time, this bracket is, we should think of it as being to the minus 3. So it's similar to this one, except because of the minus power, the bracket's going to appear underneath. So this time I'm going to try 2 plus cot x. And because this is to the minus 3, I'm going to raise it up 1 to minus 2. Okay, and then same as before, differentiate and then compensate. Right, so I'm going to differentiate this. That's going to give me minus 2 in front, 2 plus cot x. That goes down by 1 to minus 3. And then out of the bracket, the derivative of the bracket is, as we set up here, minus cos x squared x. Okay, tidy up. That gives us positive because of the double negative. 2 cos x squared x. And then because this bracket is to the minus 3, I'm going to write it underneath to match what I've got at the top. To the 3, sorry. There we are. Okay, so we almost got it, except for the 2 at the front of this. So again, we're going to cancel that out from our guess by dividing by 2. So again, I'm going to star the integral just so I don't have to write it again. And it's a half of my guess. To the minus 2. Okay, if you want, you can write that as a reciprocal, but you don't need to. That's our answer, and I'm going to plus c as well. Okay, right, hopefully we're getting the hang of this. Again, if you want to skip ahead after these and you're feeling confident, then please do so. For this third example, I've got sec squared 2x over tan 2x plus 1. And just like the previous one, I'm spotting that sec squared is the rough derivative of tan of 2x. In fact, tan of 2x is going to give me 2 sec squared 2x, but that's a multiple of my derivative. And because it's on top of this, and this has no power other than, like 3 was on the last one, right? It's of the form, let me write it this way, of the form f dash over f, right? That form is suggests that we should use ln, whereas this one has a power on the bottom other than 1, so we have to use the power rule for that one. So we're going to try ln of the denominator. I don't know why I wrote 2x in there, it's going to be tan 2x plus 1. Okay, that's our guess now. So we're going to differentiate this, see what we get, and then scale it appropriately. That's going to differentiate to, okay, 1 over tan 2x plus 1. Okay, that's my outer function. Ln goes to 1 over. The derivative of the inside is 2 sec squared of 2x. Okay, which gives us 2 sec squared 2x over tan 2x plus 1. There's a 2 at the front I want to clear away. That 2 shouldn't be there, so we're going to halve, making it this. It's going to be, right, a half of our guess, a half ln, absolute value, tan 2x plus 1. Okay, basically our guess there, but halved if you can't read that. Lovely. Okay, 2 to go. Again, looking out for the form that we've got. So this one has an x at the front, which looks like it matches up with the derivative of x squared. So that looks good. We're looking like we've got a form going there, and this bracket is to the 3. So this form is f dash of x times f of x to the n. That's the form of our integral that we've got. And in this case, what we want to do is try f of x to the n plus 1, which will then go back down to n again, and the f dash is going to come out. So we're going to try x squared plus 2 to the 4. Okay, that's going to give us differentiating again. 4 at the front, x squared plus 2, 4 goes down to 3. Out comes 2 of x from the chain rule, giving us 8x, x squared plus 2 cubed. This is 8 times what I'm supposed to be getting, because I'm supposed to be getting 1x, so we're going to divide by 8. Star that. This is an 1/8 of our guess, an 1/8 of x squared plus 2 to the 4. Again, plus c. And I've got plus c over here. There you go, plus c. Right, one to go. 5 tan x sec squared x. Now, this one's a bit of a funny one. This one's a bit of a special case. If you have powers of sec, we discussed this briefly yesterday. What you don't want to do is raise the power of sec to the n, because when you differentiate sec to the n, because of the inside derivative of sec producing another sec, it's actually going to raise the power back up again. So you want to stick with the same power this time. So sec to the n of x is going to differentiate to n sec to the n minus 1 of x. That's from the power rule. But then multiplied by sec of x going to sec x tan x. Okay, so because this sec x is going to coincide with this sec to the n minus 1, that's going to go right back to sec to the n again. I won't write the whole thing out, but we're looking at the fact that it makes sec to the n again. with other stuff around it, okay, with other stuff next to it. Okay, so in this case, what we wanted to be doing is not choosing sec to the 3, but sec squared again. So we're going to do that. Okay, now it turns out you could just as easily try tan squared by noticing that sec squared is the derivative of tan, but it's up to us. I'm going to use sec squared for this one. Okay, sec squared x differentiates to 2 at the front, 2 times sec to the 1, and then multiplied by sec x goes to sec x tan x, and that makes 2 sec squared x tan x. Okay, compare it to what we've got up here. We've got most things in the right place apart from the 5. Our guess of sec squared x gave us 2 at the front, and we're trying to get to 5, so what we want to do is scale this up by a factor of 5 over 2. So our final answer for this one is 5 over 2 sec squared x plus c. Okay, if you chose to do it my alternative way, if you did tan squared instead, you'd get a different answer to this. But for reasons that you might want to think about, these answers turn out to be equivalent. Okay, your other answer is going to involve tan squared, and you can suss out why it's equivalent to having this answer as well. Okay, right, those are 5 examples from yesterday that involves reverse chain rule, and it's pretty much by inspection for these ones. Now, if you're ready to move on with these, after getting some more practice, the next method that we're looking at today is called integration by substitution. Okay, it's something that the further maths people are going to be familiar with. So basically what this does is it takes awkward looking integrals and it gives a method for changing the variables in such a way so that your integral becomes something that's much more easy to cope with and easier to integrate. Okay, it is related to the reverse chain rule. Okay, in fact, it does everything that the reverse chain rule is doing, except you don't particularly have to do it by inspection, okay, because it's got this kind of procedural method for working through it. Okay, so I'm going to do an example here and maybe another one on another slide, and you can get to grips with how it works. So we've got this integral here. I want to integrate x times the square root of 2x plus 5, and that's dx. And it's telling me to use a substitution, which is a change in variables to u equals 2x plus 5. Okay. What that means is that in your integrand, everything that you're integrating, you want to turn everything that you've got in terms of u. Get every x in terms of u. Okay, I suppose it says it here, but I'm just writing it and talking through it. And that includes dx as well. Okay, and I'll show you what I mean by that in a minute, including dx. Okay, so here's my substitution. I'm going to rewrite the thing I'm integrating here in terms of u, and also by differentiating my substitution, I'm going to get an expression for dx as well. So step 1, using a substitution, work out x and dx. So let's rewrite this. U is 2x plus 5. Okay. Now, in my integrand up here, the 2x plus 5 is in here, and that's going to become u. The x, however, is something that I can use my substitution to write in terms of u. So by rearranging, u minus 5 over 2 equals x. Okay, and that's going to be useful when I rewrite this in a moment. And then also, if I differentiate my substitution, du by dx is equal to 2, because that's the derivative of 2x plus 5 with respect to x. And what I now want to do is rearrange this by considering these derivatives symbols here to be a fraction, which you're allowed to do. I'm going to times by dx and put it over on this side with the 2. And I'm going to divide the 2 back again to make a half du. Okay. Okay. So for the time being, just consider the fact that you can treat these as fractions when you're doing this manipulation here. Okay. So dx is a half du. Now all of these bits are going to go back into my integral, and we're going to replace all of the x's for u's. Okay. There shouldn't be any x's left over when we're done. So I'm going to style this and rewrite it. So now we're integrating x, which is, according to this, u minus 5 over 2. Then the square root of 2x plus 5, but we said that 2x plus 5 was going to be u. And then dx, which is going to turn into a half du because of what we did over there. Okay, so these 3 bits here correspond to the 3 bits that we've got at the top, just using all of our rearranging in here. Now, what should have happened is that our integral is now more manageable. And what I'm going to do now is I'm going to factor out any constants that I can see and make it a bit easier. So there's a 2 on the bottom here, a 2 on the bottom here. That's going to combine into a quarter, which I'm going to write on the outside. Then I've just got u minus 5 at the front. And then root u, which I'm going to write as u to the half because of the next step. And now we're integrating du. Okay, so my entire integral is written in terms of u. Now the next step is to integrate my new simplified function, but I'm integrating with respect to that new variable u. So treating u as if you were treating x previously. The quarter is going to be at the front, and then I'm going to integrate, but I can't integrate until I've expanded this bracket. So this is u to the 3 halves minus 5 u to the half. Okay, remember powers add, so when you times these together, it's 1 plus 1 half, which makes 3 halves. Now I can integrate. My quarter is going to stay at the front. And then just using the power rule, I can integrate these u's. So we've got a quarter. U to the 3 halves goes up to 5 halves, and then we divide by 5 halves. Minus 5, u goes up to u to the 3 halves, and then you divide by 3 halves. And then we're going to add c. Right, let's tidy up these fractions. So remember, dividing by a fraction is the same as flipping and timesing, so I'm going to flip that 5 halves into 2/5. If I multiply 2/5 by a quarter, maybe I want to write that down first. 2/5 times a quarter, that's going to be 2 20ths, which makes a 10th. So I'm going to write that as a 10th. 1/10 u to the 5 halves. And then dividing this by this 3 halves is going to be timesing by 2/3. That's going to turn this into 10/3. Use the 3 halves plus c. Okay, so now I've integrated and simplified in terms of u. The final step is to undo your substitution and return back to everything in terms of x, because our initial integral wanted us to integrate these x's, so we're going to go back to doing that. So remember, u is 2x plus 5. That goes into both of these u's here. And don't worry about my phone. I don't know why it's going off all the time. Right, final step, a 10th. U is, I'm going to rewrite in blue, that's 2x plus 5. That's to the 5 over 2, minus 10/3, and then another 2x plus 5. And that's to the 3 over 2, and then plus c. And then we're done. Okay, so it looks as if this isn't something that you'd be able to do by inspection because of how complicated this answer looks, right? It's unlikely that you'd be guessing this bracket to the 5 halves and this bracket to 3 halves in order to produce this. So in a question, it's likely that they're going to tell you which substitution to use, and then you've got to work through the steps to get to your final answer. Okay? If you're not given this substitution, then normally it's reasonably obvious what one to pick. So by looking at this, the bit that's the most awkward, if you like, is the bit that's inside this square root, the bit that's kind of more difficult to get access to, which is this bit inside here. That's going to be a substitution. That's generally a rule of thumb. Okay, right, let's see another example. Before that, though, there's a slide here on what our sensible substitution is going to be, just based on what I just previously said. So looking at what we've got, if we were to do this by substitution, you'd be picking, for this first one, the awkward portion is this bit in the square root, so I'll be using u equals 1 plus sine x, and working from there. For this part, now this is one that you could do by inspection, but doing it by substitution works just as well. What you'd want to do for this one is make your u be this awkward power, which is x squared. For this one, the bit that's getting in the way here is the denominator, so I'm going to make u be 1 plus x. And for the final one, we've got this horrible power of e with a expression in x, and that's what's going to be our u for that in that case. Okay, it's going to be that awkward power of e that's then going to simplify when I turn it into u. Okay, so that's a bit of an idea as to how this is going to work. Right, second example before you try some yourself. So we're going to use u equals sine x plus 1 to integrate cos x times sine x times 1 plus sine x cubed dx. Okay, so it's the same steps as before. I'm going to try and get everything that I've got here in terms of u's, including dx. So I'm going to write out my u again. This time I'm going to do the differentiation first, just so I can make sure I can get to dx. So differentiate u with respect to x, that becomes cos x. 1 disappears to 0. Solve for dx, du equals cos x dx. And then dividing by cos x gives us du over cos x equals dx. Okay. Now you'll notice that what I've got here still has x's in. However, when I rewrite my integral in a moment, the over cos x is going to cancel out with the cos x that I've got over here. So not to worry, it should all sort itself out when you put it together. Okay, I can write 1 plus sine x in terms of u. I can also write this sine x term in terms of u as well. I'm going to do that as well. So u minus 1 is sine x. That's going to help me rewrite this portion up there. And cos x, we've kind of referred to a moment ago, it's going to cancel in a minute when I write this du over cos x. Okay. Right, substitute into the expression. This is step 2. So now I'm going to rewrite this star. And it's cos x. Currently can't write that in terms of u. Sine x is given up here, u minus 1. 1 plus sine x cubed is just the same as u cubed. And dx is du over cos x. Okay, and then praise the Lord, cos x there cancels with this cos x down here. Okay, now to save a step, what you could do is spot that this cos x dx appears up here in your question. The cos x dx appears there, so you could just look at those blue bits and replace it with du, but the same things happen down here with this cancelling. Okay, continuing now, I'm going to just rewrite this without the stuff that's cancelled out. So this is u minus 1 times u cubed, expand the brackets, u to the 4 minus u cubed, integrate du. To integrate that, it's just the power rule on these u's, u to the 5 minus u to the 4, divide by the new powers, plus c. And then in terms of x, we're going to go back to our substitution and replace with x's. So this is sine x plus 1, or 1 plus sine x, your choice, to the 5 over 5, minus sine x plus 1 to the 4 over 4 plus c. And that's your final answer. Okay, right, hopefully those examples have been all right for you and you've gone through it and understood. So I'm going to attach some examples and some practice for you to do. You're welcome to use this PowerPoint and have a look through it in your own time and see if there's any examples you want to try for yourself. And if you've got any other questions, then please let me know and I'll be there to answer it for you. Thanks very much, Year 13. Hope you enjoyed the video and I'll see you again sometime soon. Bye now.